Hello, everyone. The following is the second in a series of lectures covering Chapter 37. Today, we are going to talk about phase changes happening due to the reflection of light waves. So, you may recall that waves in a string can get reflected upside down or the right side up, depending on how the end of the string is. The same thing can happen when light reflects off a surface. So, in this case, you have a real source of light emitting two beams. They are monochromatic. The color of the beam is just there to label them. And one beam hits the mirror and then reflects off to meet the red beam at point P. Now, since with the wave model of light, we have expected light to behave like waves and interfere constructively or destructively, then we would also expect that in the same way that mechanical waves can reflect off the right side up or the upside down, that light waves also, when reflecting off surfaces, can end up being reflected upside down or downside up. In other words, reflection can shift the light wave out of phase. And that's what happens actually in this case. When the light hits the mirror, it gets reflected 180 degrees out of phase. So if the path difference between the red and the blue beam is an integer of light, it's an integer of the wavelength of light, then the point where they meet will be a dark spot because the blue beam's out of phase to the reflection. If it weren't for the reflection phase shift and their path difference was a multiple of the wavelength, then yeah, they would be both in phase. It'd be a bright spot, but the mirror flips the blue beam around, causing destructive interference at that point. So this is exactly what we've seen in mechanical waves, right? When a wave hits a hard end, it gets reflected back upside down. It gets inverted, completely out of phase. And when a wave hits a free end, it gets inverted in phase. It just gets reflected back the way it came. The equivalent of that, of a wave on a string hitting a hard end, like a hard wall, where it gets reflected upside down, is light rays getting reflected off a surface with a higher index of refraction. So when light from air hits a mirror or hits a surface of water or glass or anything like that, the light beams get reflected out of phase. The equivalent of a mechanical wave on a string reflecting off a free end and just coming back the same way with the same phase is when light reflects off a surface with a lower index of refraction. So light from a pool hitting off the surface with water, light gets reflected in phase, so there's no phase change. So if light hits a more dense medium, that's like a wave hitting a wall, gets reflected out of phase. If it hits a thinner medium, it's like a wave hitting a free end, it gets reflected back in phase. This is why we see cool rainbow patterns on soap bubbles. Basically, some light gets reflected off the top of the bubble, and some goes into the bubble and reflects back from the underside of the bubble, and they come back at you. So all these rays are coming in at different phases due to the phase change by reflection, and different parts of the bubble then have different colors of light that are more intense than others. So the different colors of light are interfering throughout different points of the bubble by different amounts. So due to the interference of the light rays, at some point certain colors are more intense than others. We also see this effect, again, like on the feathers of a hummingbird, where different parts of the feathers have different colors with dominating intensity. You can also see this when you have, after it rains, you have water on the pavement. So you have kind of like water being between two mediums, right? The air on top and the pavement below it. Now, On the example on the left here, it's kind of a similar idea. It's oil sandwiched between the air and water. But the same thing happens when it's just water between air and the pavement. You see, right, the cool little rainbow pattern on the picture on the right that you may have seen after a rainy day on the streets. So what's happening in this case actually is that there's, part of the light gets reflected at the top of the oily surface, at the top of the water on the pavement, and part of the light gets reflected from the bottom. In this case, both parts are actually reflected out of phase, which means relative to each other, they're actually in phase. So if the path length between them is a multiple of the wavelength, then they'll interfere. They'll interfere constructively. So to sort of mathematically describe the conditions for interference from a thin film, let's consider a flat lens of some material sandwiched suspended in air. So air has an index of refraction of almost 1, like a vacuum, like free space. And you're going to shoot a light beam from the top, and it's going to hit the film. We also know how thick the film is. We also know its index of refraction is n, its thickness t. So what's actually going to happen with the incident light ray is that the incident light beam will actually reflect and refract at every time it meets the boundary between the film and the air. However, every time it does so, its intensity gets split between the ray that reflects and the ray that refracts. So it keeps losing intensity as it creates more rays. Theoretically, there's an infinite number of rays that spread out off the film, but the most intense ones are coming from the first instances of reflection and refraction. So we're only going to focus on the first two rays that reflect back up through the top of the film when we talk about thin film interference. In the case of the schematic shown on the right, we're only really going to discuss the first reflection, which is ray number 1, and then the second reflection that occurs from the part of the incident ray that transmits into the film and reflects back up through the top from the bottom of the film. So ray number 1, because it hits a denser surface, gets reflected out of phase, but ray number 2 gets reflected in phase because it's hitting a surface of air with a lower index of refraction. Now, that won't necessarily determine if they how they interfere. We also need to consider the path length between them. So there's a bit of like horizontal and vertical difference between the distance traveled by ray 2 and ray 1. But as an approximation, we're going to assume that the rays are close enough to the normal, that the horizontal difference in their path length is insignificant. And what really matters is the kind of like extra vertical distance that ray 2 covers. The extra distance ray 2 covers then, since the ray goes down to the bottom of the film and then back up, is twice the thickness of the film. But also we have to consider the fact that while traveling in the film, its wavelength changes by a factor of 1 over the index. So having accounting for that, in the case that the two rays emerging from the top of the film and they're relatively out of phase when they emerge, they will interfere constructively if the path difference between them is a multiple of a half wavelength. So the formula here accounts for the path difference, which is twice the thickness, and it also accounts for the fact that one ray is relatively out of phase with the other due to reflection. If you're looking for how thick the film or the lens has to be for destructive interference, then it must be thick. So it must be at a thickness that the path difference between the ray 1 and ray 2 is a integer multiple of the wavelength in the film. Right, because 1 and 2 are relatively out of phase when they emerge. So if they were to just meet without having traveled different path length, they will destroy each other. And that's because, again, of the phase difference due to reflection. So every time that the ray 2 travels a distance that's a multiple of the wavelength, it's going to meet ray 1 totally out of phase, because that's how they start off. Now, there's another situation where both rays get reflected out of phase, or maybe they don't. So for example, in this case, a thin film is silicon oxide, and ray number 1 gets reflected out of phase, and so does ray number 2, because the bottom of the silicon oxide is touching silicon, which has a higher index of refraction. So this acts as a hard wall for ray number 2, so ray number 2 also gets reflected back up out of phase. So ray 1 and ray 2 emerge from the top of the silicon oxide relatively in the same phase. So they're both out of phase with the incident ray, which means that they're both in phase with respect to each other. In that case, the phase change due to reflection is not a factor anymore. And so to determine whether they will meet and destroy or construct a brighter spot depends on the path difference. And since they're emerging in phase, then constructive interference happens when the path length, which again is always twice the thickness of the film, is a integer multiple of the wavelength, and destructive interference is when it's a half wavelength multiple. So when both rays are relatively in phase, you can use these formulas for constructive and destructive, but when one of them's out of phase with the other, you flip the formulas. Okay, so quick quiz. You have 2 microscope slides, so that like the leftmost edge of each is kind of, they're watching a little human hair, so you can look at the hair and zoom in on it, see what it's like. And there's just a little thin wedge of air between the slides due to kind of like the hair being there between them, right? Creates a little space between the 2 slides. So the question is, what kind of interference pattern is going to occur? And in this case, this kind of flips the idea of a thin film on its head. Now you have a thin film of air wedged between suspended in glass. So there's glass on top, glass on bottom, and there's just a thin film of air in the middle. So some light's gonna reflect off the top part of the film of air, and some's gonna reflect off the bottom. The light that reflects off the bottom, sorry, the light that reflects from the top is coming from the glass and reflecting off air. That's like a wave on a string hitting a free end, right? Because air is less dense than glass, so it's going to reflect, it's going to keep the same phase. There's going to be no phase change. But the second ray that goes through the interface and goes to the bottom of the air wedge and then reflects back up through the top, that one's reflecting off the slide at the bottom, which is denser than air. So when it does that, it's going to come back up out of phase. So the ray that comes off the top and the ray that comes off the bottom are coming out of phase with respect to each other. Now, whether or not the interference pattern will be a dark fringe or a bright fringe depends on whether they are meeting in or out of phase. That also depends on the path length. And the path length is, depending on the thickness. But in this case, right, the thickness is of the film. This is just like a little tiny wedge of air due to the hair being sandwiched by the 2 slides. So its thickness physically 0. So basically, the path difference between the 2 rays is just non-existent. So the only thing that sets them apart is when one's out of phase with the other. So they will arrive at any point, and they'll be out of phase. So you would see a dark fringe since they would start to cancel each other out. Anyways, that's all for now. So hope you join